In the previous video, we talked about the differences between data science, machine learning, deep learning versus AI at a very high level. In this video, we are going to talk about some of those specifics. We'll take a couple of examples and try and understand it. We'll take a couple of examples and try and understand them at just a little bit more depth. Now, we'll not be running any code. We'll just be conceptually looking at some of the data sets and what we can infer out of them. Let's take a simple data set. A data set everybody would understand. We all go to supermarkets, right? Convenience stores, whatever you want to call them. There is typically data like this. So if you go to a supermarket, all the data is recorded like this. So this is the order number. So 10001, 10002, so on. And then there will be, for each order, for example, 10002 has 2 line items, meaning somebody who just placed this order purchased 2 line items. Say, this is our item number, and that item is going to be 12012, and this is going to be 14084, just 2 items, and their description, this is item description. I'm giving the details only for this order, not for this order. So the description of this item is going to be say diapers and beer. This is actually a classic case, a combination of beer and diapers. We'll revisit it in a bit. And then there's price, right? Diapers is say $10 and beer is, let's say, $15. And the list goes on and on and on, whether he's a member or not. If he's a member, then we know some of the details like is it a male or female? So say this is a male. Yes, he's a member. And so on and so forth. There will be probably somewhere close to 100 fields that we capture for every single transaction in a supermarket. This is our data. Now, what can we infer out of this? What can we make out of this? What intelligence can we draw out of this? There are many things, but we're just going to look at 3 or 4 different examples. Say somebody at the corporate level wants to promote some coupons, and they want to understand whether the coupon should be focused more towards items that are male oriented versus female oriented. I'm not being sexist about it. This is what supermarkets do, or any company does. For example, does it make sense to invest more in marketing male shaving products versus baby formula, which is something that more females would be inclined to purchase? The answer to this question depends on who does most of the purchases. Is it male or is it female? Depending on the member information that you have, you can draw some inference from this saying. You can just draw a plot like this and say, this is the sales. Give me the total sales for male versus female. This is the total sales. So in this case, most probably females typically dominate this particular data set. So most sales are done by females. This is female and this is male. So obviously your marketing strategy is more focused towards females, right? Let me revisit this example. Sometimes these supermarkets are interested in something called as a combos. What is a combo? Well, you tend to sell products together. An interesting use case that has been found out based off of the supermarket data sets is that beer and diapers go together. Well, how do you know that? Well, there is a machine learning algorithm, well, a couple of them, called a priori. This algorithm can identify pairs of products that sell together. For example, beer, diapers. This was actually a surprising find. What supermarkets have found out is that in the afternoon, when males tend to come home and go for shopping, they go buy beer, but at the same time, if they're married, they tend to buy diapers as well. So what the supermarket has done is placed beer and diapers together. That way, increase the sales and make it more convenient for the user as well. Right? This is a classic case. Many such sets, rather, can be extracted using machine learning. Like, for example, there's milk and say cheese or cream cheese, right? Another example, or strawberries and cream. Well, we know strawberries and cream go together, but our machine learning algorithm based on this data set can infer this for us based on the total number of sales and how they go together. There's a whole bunch of math behind it. But the point being, this is a classic example of using ML to predict patterns that you don't normally see. You give this data set to anybody, however large the data set is, it's unlikely that you're able to find these patterns. Well, at least an untrained human eye. Even for a trained human eye, this is very difficult. Another example. This is specific to members. Based on their buying pattern, can we identify if he's a member or not? Now, the reason why we would want to do that is we want to predict and sell more to members or non-members, depending, right? Or based on this buying pattern, can we upsell anything to a member? So, or rather, based on this buying pattern, can we identify if a typical purchase, an average purchase of a member is greater than $50 or less than $50, right? So this is a prediction. There's no hard and fast rules for it. And this can be done using a variety of ML algorithms. I'm not going to the details of what ML algorithm you can use. You can use logistic regression or some kind of a classification algorithm, right? So it would go something like this. So item. So what are the parameters that we have? We have item and we have price, membership, yes or no, of course, male or female, right? Based on this, can we identify if the user is purchasing, if the average purchase of the user is greater than $50 or less than $50? And what decisions to make based on the fact that if it is greater than $50 or less than $50 is something that the marketing department can take. But what I'm trying to say is, can we predict based on these predictors if, and this is the value we're interested in, is it greater than 50, less than 50? It's basically a classification problem. And it can be done using a variety of ML algorithms. So this is again a case of prediction. The point I want to make here is that this is an example of analysis, while 2 and 3 are examples of prediction. All of these are data science, but mostly this is machine learning. This is machine learning, while this is not machine learning. This is just analysis. So purely in terms of data science, if you're trying to analyze the past or explain the past, it's called analysis, and this is part of data science, but not machine learning. Okay? But in cases like this, where we are trying to predict the future or future buying patterns, any of that stuff. When you're trying to predict, this is classic case of ML. And it's also data science. Because data science can be used either to explain the past, in this case, or predict the future, in these two cases. Over here on this slide, we are trying to explain the differences between machine learning and data science, and what data science covers and what machine learning does not cover. In the next slide, we are going to specifically talk about deep learning. So in the previous slide, we've talked about data science, the scenarios it covers, versus machine learning. So DS versus ML. Now we're going to talk about deep learning versus machine learning, or rather just focus on deep learning. Let's take a simple example. Say there are a list of numbers. So these are the list of numbers, column 1, and column 2 identifies if those numbers are odd or even. We know how to identify an odd number versus an even number. Just divide them by 2, and if you don't get a reminder, it's an even number, otherwise it's an odd number. Machine learning or deep learning can identify a pattern like this without doing explicit logic. Like in this case, the mathematical logic is percentage 2 or modular division by 2. If it is equal to 0, it's even, otherwise it's odd. This is something that we know of. So there is no need for machine learning in this case or deep learning. But in cases where the pattern is not mathematically clear, like so, we fail to identify what the pattern is. If you want to go with standard mathematics or any other kind of logic, that's when statistics in the form of machine learning comes to help us. Now, in this context, I want to talk about deep learning because I want to take a simple use case first, and then I'll talk about a more involved use case. How does deep learning solve this example? The input in this case is just one number, right? It's just a number. So the input is a number. Right? And then the output is a classifier. This will say 0 or 1 depending on if the input is an odd number or an even number. Right? In between, what we have is a hidden network, a network of nodes. Now I've drawn 6 nodes here in 2 layers. That's purely arbitrary. There could be n number of nodes, n number of layers, and that's not an exact science. People typically do a trial and error to find out how many nodes works best for the corresponding problem. In this case, what happens is these nodes are connected. All these nodes are connected with all the other nodes. That's how typically it works. And finally, the output is obtained. Now, the way this works is, say for example, you give an input of 3. Okay, and then there is a weight here. A weight could be 0.03. This could be 0.5. This could be 0.09. Right? And then 3 or whatever output, there is a function here, f of x, right? Doesn't matter what that function is. There is an output that's triggered out of this, right? And then that's multiplied by the corresponding weight and it goes and sits here. And the output of this is multiplied by a corresponding set of weights, 0.09, 0.3, 0.2. And the output from both these 3 nodes, or rather all these 3 nodes, will come and sit in this node. right? And the output from this goes here all the way until the final node is obtained. Now this is deep learning. The reason why it's called deep learning is because these layers are deep between the input and the output. There is a set of hidden layers, and that's why it's called deep learning. All the logic lies in these weights, and these are called, this f of x is called as an activation function. Now I don't want to get too deep into deep learning at this point, but the point being, this is a network that we can't explain. And the structure of this network, where the weights are multiplied into the corresponding nodes, these are called neurons. And the structure of this neuron and neural network is something that has been inspired from the way the human brain is structured. Not the way the human brain thinks. People still don't know how the human brain thinks. But the neural network is structured based off of how the neuron inside our brain is structured. So the structure is something similar to this. There are inputs, and then inputs go to a neuron fires, and that goes to another neuron, and finally until you obtain a result. Now, the best part of this is, nowhere in this architecture are we defining a standard operation like this. We don't have to define it. The network will define the problem and the solution by itself. That's the beauty of a neural network. Now, this can be expanded to any kind of an arbitrary problem. Now, the problems that neural networks can solve are not limited to just simple problems like this. Image classification can be done using a similar set of networks. The only thing is, the size is going to be very big. For example, if you take an image, a simple image in a Tesla car, for example, because we know that's a good example of self-driving car, a single image, maybe from the rear, okay, could be, let's say, 5 megapixel. That's 5 million pixels. What can we do with 5 million pixels? Well, there is a whole lot of optimization that we can do here using CNNs, convolutional neural networks, so on and so forth. But the way it works is exactly similar. Instead of just one single input, you have multiple inputs. Each input corresponding to a pixel. And finally, and in the middle, there's going to be a deep network, many layers large. It could be 10 layers, and each layer having probably somewhere close to 250 or 300 different nodes or neurons. And finally, we could have multiple outputs. The example I've explained previously is just with one output, whether it's an odd or even. In this case, we are talking about multiple outputs, which classify at a high level whether it's a moving object, whether it's a car, different examples. The examples would depend on what they want to see, really. On the rare, what do they want to see? They want to classify a road separately, they want to classify a car separately, they want to classify a person separately. Each of them can be classified separately. Or they want to just classify as stop or go, because the situation would demand that irrespective of the object, the car should either stop for that obstacle to move, or otherwise it can freely move, right? It could be a classification problem, or sometimes it could be a regression problem. Like, for example, calculate the distance. Identify the distance. If it is less than 1 meter, stop. If the obstacle is less than 1 meter, stop, otherwise go, right? That's an example of a regression problem, not a classification problem like this. So these are examples of deep learning. And the way deep learning works, technology-wise, is totally different from the machine learning algorithms. But purely in terms of classification, deep learning is a subset of machine learning. And remember, all of them are typically subsets of AI. And we know where data science fits. The moment you try to explain the past using analysis, that's still data science but not machine learning. The moment you try to predict the future using data, it's still data science, but it can also be machine learning or deep. Because the difference between machine learning and deep learning is just in the technique. But otherwise, deep learning is just part of ML. I hope this makes things clear in terms of the differences between data science, machine learning, deep learning, and AI.